Why do we have the unit circle? Well, let's talk some physics. This might hurt your brain a bit. So imagine, if you will, this setup right here, okay? And we have a roll of paper that's going to be rolling, going in this direction. We have some lights, and there's a ball. And what's going to happen is this is light-sensitive paper. So if it's not receiving light, then you're going to go ahead and show it. Okay? Everything else that's being exposed to light will become dark. And what happens is when we go ahead and allow this to rotate, okay, you notice that this is rotating on this wheel. As this rotates, our view of this from the side, as far as the lights are, if you're these lights, right, here are the lights, 2, 3, 4, okay. And what they're looking at is, this is what they see. They see the turntable, the rectangle part right here. Then they see the disc on top, this right here. And then they see the ball on top. This is what the lights see. And all they're seeing is just seeing that ball go back and forth, left and right, left and right, left. From above, we know this is going in a circle. But from a side view, all we see it doing is going back and forth, back and forth. And so as this ball is going back and forth, left and right, according to the lights, and this roll of paper is going up, it's actually forming this graph. Okay. Now this graph, if you've seen it before, this is the sine graph, or it could also be the cosine graph. Okay. We're not going to graph for a cool while. Okay. But I need you to recognize what's happening here. Okay. Now, what does this got to do with the unit circle? Well, check this out. What if, let's see, this is a cosine. Oh, this is hard to do. Okay. Let's say this is the y-axis and this is the x-axis, right? Recall from your unit circle, what is the value of x at 0? So what is a cosine of 0? What is the value of x? At x, at 0 degrees, x was 1. So if you look up here, here's 1, right? This is 0. This right here is going to be 90 degrees. This right here is going to be 180 degrees. This is going to be 270. And this will be 360. And hopefully you finished completing your whole unit circle like I suggested. Now, if you look at those, just those 4 points, right? You told me that at 0, x was 1. Hopefully at 90 degrees, you remember that x was 0, which it is, right? Here's 0. Then at 180 degrees, you probably told me x was -1. Here it is at -1. Then at 270 degrees, x is probably 0 again. And spoiler alert, 0 degrees is 360 degrees. Now you'll notice that in this graph as well, that the x value, as it gets bigger, then the y value is getting smaller, just like we predicted before. So what happens is that this natural phenomena of things going back and forth, right? A pendulum, a clock, a swing, all the planets, okay? The seasons, the days, the sun, all these things follow what we call a cyclic motion, okay? And is actually a periodic motion because it has a period. And it's all the unit circle, okay? Let's show you a simulation. No damping, because that's pretty advanced stuff. Damped model oscillation is going to be something you learn in advanced calculus called partial differential equations. Let's see, rulers, sure, timer. Timer is a good idea. No, reference line. That's good. Okay, cool. Okay, great. So you'll notice that this bar is going up and down, back and forth, back and forth. Okay, again, this is not turning in circles. This is going up and down, up and down. This wheel right here is going in circles. Okay. You'll notice that a wave is being formed. You'll notice that there is an x-axis and there is a y-axis. You'll notice a few things that when I go ahead and I can change the amplitude, and you tell me what the amplitude is. I would propose to you that the amplitude isn't what you think it might be because there's still the same amount of waves. See, there's a point right here. There's a point right here where it's just on the x-axis and a point right here, right? So even though I may change the amplitude, I'm still hitting those same spots. So the amplitude does not affect how many waves you see, but what it does affect is what? Now, if this is a sound wave, you have an amplitude button on your remote control, on your TV remote, okay? And it's called volume. So if you increase the amplitude of your sound wave, you're going to hear more of it. And if you decrease the amplitude of your sound wave, then you're going to actually hear less of it, okay? So that's what amplitude does. Frequency, on the other hand, frequency is what you thought it was going to be. Notice now that I'm totally hitting this in a lot more spots than before, right? So I do have this spot and this spot and this spot, but now I have additional spots that are hidden in between. So there's one right here and another one right here and another one right here. So I've doubled the frequency from what it was before. Okay. Now that doesn't matter. What matters is the following. What does this have to do with the unit circle? Well, it's going to go backwards, but check this out. Remember, this is the x-axis. This is the y-axis. And let's do cosine. This works for sine as well. But the funny thing is we always teach you sine first, but cosine is actually what we use more in nature. So when you go and do, when you go to the hospital and you see that EKG machine going beep, 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 right? That's actually a cosine function. All right, so we tend to use cosine a lot more in nature, and this is a good example of that. So here we are again, right? This is your unit circle. Actually I'm tripping. This one might be sine. Let's start off at 0. My bad. I think the way they made this one, usually it would be cosine, but the way they made this looks like it's a sine. It's a sine. All right. They're gonna do this in a weird direction. So I'm gonna speed this up for you. Here's 0 degrees slash 360, 270 down here, 180 over here, and 90 over here. So let's look at sine this time on your unit circle. Let's look at sine. Okay. What is the sine of 0? If you look at, and this time we're looking at the y value, right? We're looking at the y value. So right now, the sine of 0 is going to be at 0. Here's 0, and 1 is going to be up here. And then negative 1 will be down here. So I know the whole wave is going, but all I want you to do right now is to kind of focus on this right here. So the sine, we're going to do sine. The sine of 0 is 0. What is the sine of 270? Well, I have this little dot now at 270 degrees, and you'll notice that it's actually at negative 1. And on your unit circle, it should be negative 1. If I go ahead and step this over and move this little point to the 180 mark, we should get too far, sorry. We should get that the sine of 180 is 0. And then when we hit the sine of 90, when I make this point go all the way to the 90 mark, you'll notice that it's at its maximum optimal height, which is going to be 1. Sine of 90 is 1. And then we go ahead and repeat, and we're back to 0. And we know that sine of 0 is 0. Okay, so the unit circle isn't something that we, unfortunately, mathematicians and math teachers, they teach it in a very dry, boring way, like what does it got to do with anything in life, or with trigonometry or triangles in general. But it actually comes from nature. Okay, something that happens all the time. Your heart rate is cyclic, it's periodic. The rotation of the planets and all that kind of stuff is cyclic in nature. Okay, so hopefully you have a better understanding of, excuse me, of the unit circle and where it comes from and what it really means. Okay. Oh, here's another picture. Oh man, all these pictures. So in this case, oh, springs. Anytime you have a spring, this one is actually nicer. Here we have a spring and there's a pen attached and there's a paper that's rolling down. So the paper is being rolled down this way. And we compress the spring with the pen. The pen's attached here is writing right here. And we let it go and the spring goes back and forth. But as this happens, the paper goes. You've seen these before, right? These are the seismic graphs, right? For earthquakes. So an earthquake machine works on this principle. Sinusoidal is essentially that sine shape, right? Or that cosine shape, that shape that's going this back and forth, right? The ocean waves are cyclic, right? That's sinusoidal. How does this graph compare to the one from problem 5? Gee, oh, it's the same one. Yeah, they're all the same. I should know that. Gosh. Okay, great.